What if a computer could explore every single possibility, all at the same time? I know, it sounds like science fiction, right? But it's the very real promise of quantum computing. And in the next few minutes, we're going to break down the three, frankly bizarre quantum principles that make it all possible: superposition, entanglement, and interference.
So, here's how we're going to tackle this. First, we'll talk about the huge leap from our regular computers to quantum ones. Then, we'll get into those three big ideas one by one. And finally, we'll see what it all means for our future. Let's jump in.
Okay, so to really get why quantum computing is such a game changer, we first have to talk about what's holding back the computers we use every single day.
Think about a computer trying to solve a super complex maze. A normal or classical computer, it's going to try one path, hit a dead end, go all the way back, and then try another. It works, but it's painfully slow. Now, a quantum computer, it could explore every single path at the exact same time. That's the mind-blowing difference we're talking about here.
See, the phone or laptop you're using right now runs on bits, and a bit is just like a light switch. It's either off, which is a 0, or it's on, a 1. Simple, right? But quantum computers use something called a qubit, and thanks to the wild rules of quantum mechanics, a qubit can be a 0 and a 1 at the exact same time.
So, how in the world can something be two things at once? Well, this brings us to our very first core quantum principle: superposition.
Superposition basically means a qubit can be in a mix of both 0 and 1. It's not one or the other. It's a whole range of possibilities all at once. And this one idea is the secret sauce. It's what gives a quantum computer this incredible power to work in parallel, exploring millions of scenarios instantly.
You know, a really great way to picture this is a spinning coin. While it's up there, flipping in the air, is it heads or tails? In a way, it's kind of both, isn't it? It only picks a side, heads or tails, when it finally lands and we look at it, when we measure it. A qubit in superposition is exactly like that spinning coin. It holds all its potential answers at once.
And here's where it gets absolutely nuts. This power grows exponentially. So 2 qubits can hold 4 states at once. 3 qubits can hold 8. But get this, with just 300 qubits, you could represent more possible combinations than there are atoms in the entire known universe. I mean, that's not just a big number. That's an explosive level of power that classical computers can't even dream of.
Okay, so superposition gives us this ridiculously huge space of possibilities. Our next principle, entanglement, is what connects them all together in a really strange and incredibly powerful way.
Entanglement is what happens when 2 or more qubits become, well, linked. They're inseparably tied together. Their fates are intertwined and they behave like a single entity, even if you put them on opposite sides of the galaxy. You measure one and you instantly know the state of the other. This connection was so weird, so counterintuitive, that Albert Einstein himself famously called it spooky action at a distance. He just couldn't wrap his head around it, but guess what? It's been proven to be absolutely real, and this spooky link is a critical resource that gives quantum computers their edge.
So the key thing to get here is this. If you have 2 entangled qubits, the second you measure one and it turns out to be a 0, you know instantly that its partner is a 0 too, no matter how far away it is. This creates this deeply connected system that allows for calculations so complex they are just impossible for any regular computer.
All right, so superposition creates a massive space of possibilities, and entanglement links them all together. But with millions of potential answers floating around in there, how do we find the single right one? That is where our third pillar, interference, comes into play. Interference is basically the quantum computer's secret weapon for zeroing in on the right answer. It lets you manipulate the probabilities of all those states in superposition. You can literally amplify the signal of the correct answer, while making all the incorrect answers just cancel each other out.
Think about waves in a pond. When 2 wave crests meet, they join up and make a bigger wave, right? That's constructive interference. But when a crest meets a trough, one up, one down, they cancel each other out. Poof! That's destructive interference. Well, the probabilities in a quantum computer behave just like those waves.
So a quantum algorithm is like a carefully choreographed dance. It's designed to guide all these probability waves so that the wrong answers all run into each other and cancel out through destructive interference. At the same time, all the paths leading to the right answer reinforce each other, making that the one you're most likely to see when you finally take a measurement. Pretty clever.
So let's bring it all home. These 3 principles, they aren't just separate party tricks. they have to work together in a very precise way to get the job done.
First, superposition kicks the doors open, creating that huge parallel workspace to check out every possibility at once. Then entanglement comes in and links all those possibilities into one giant interconnected system. And finally, interference acts like the ultimate filter, canceling out the junk and boosting the right signal until the correct answer is all that's left.
Okay, so why should you care about any of this? Because this new way of computing could help us solve problems that are basically impossible today. Think about discovering new medicines. Simulating complex molecules is a perfect job for superposition. Or trying to optimize global supply chains with a dizzying number of variables. This isn't just about building faster computers. It's about inventing a completely new tool for discovery.
Now, we have to be real here. We're still in the very early days. We're currently in what's called the NISQ era. That stands for Noisy Intermediate Scale Quantum. It basically means that today's quantum computers are powerful, for sure, but they're also super fragile and can get thrown off by the tiniest bit of noise, like heat or vibrations. The big challenge right now is making them more stable.
But that brings us to a final, really powerful thought. We are building machines that operate using the fundamental rules of the universe itself. Yeah, they're noisy and imperfect today, but progress is moving incredibly fast. So the real question isn't if we'll build a fully stable quantum computer, but when. What happens to science, to medicine, to our entire world when the noise finally fades?